So with functions of several variables, we've seen how to find derivatives of them, introducing the partial derivative. Now we've done that, what can we do with it? Well, we know with normal differentiation it tells us a lot about the shapes of a curve, and of course partial derivatives tell us about the shapes of functions as well. One important consideration is to think about maxima and minima and associated points called saddle points on surfaces. Let's begin by considering the following function. Consider the function y squared minus x squared. And this translates into a surface that looks a little bit like a saddle. Let's consider then the partial derivatives of this function. Now, for functions of one variable, we saw that where the derivative was equal to 0 or didn't exist, turned out to be important points for the function, critical numbers of the function. For functions of several variables, we have a similar sort of thing. However, in this case, we notice that at the origin, at the point x equals 0, y equals 0, both derivatives are 0. The x derivative and the y derivative of this function are 0. Does this correspond to a maxima or a minima, or perhaps something else? So it's instructive to draw curves along x equals 0 and along y equals 0 to see what's going on. And along y equals 0, we just have z is equal to minus x squared, which is just an upside down. And along x equals 0, the function z is just y squared, so it's a parabola going upwards. So these two things mesh together to form a paraboloid in 3 dimensions. Here we have on the left-hand side, along y equals 0, we clearly have a function which looks like it should be a maximum. And along the y direction, at the origin, we have a function which is a minimum. So in 3 dimensions then, this 2-dimensional surface has a new type of feature called a saddle point, and it doesn't correspond to a maximum or minima. In general, where the derivatives are both equal to 0, we have either a maximum or a minimum or a saddle point. The general expression for a type of point like this, where the first derivative in the x and y directions is both 0, is a critical point of the function. Let's have a look at a similar type of function that we had before. F of x and y is x squared plus y squared. So it's just a sign change from the paraboloid that we looked at earlier. This is a parabola that goes upwards in both directions. It's always positive everywhere. And we can see that the first derivative in the x direction is 2x, which at the origin is 0. And the first derivative in the y direction is 2y, which at the origin is also 0. So 0, 0 is a critical point. And it's clearly a minimum because the function is positive everywhere. And since the function value at x equals 0, y equals 0 is 0, this must be therefore a minimum. It's bigger than that value everywhere else. So along both x and y directions we have a parabola. So the question is, how do we classify these critical points? It's not as simple as it is for functions of one variable, but there is a general rule to do it. It's an extension of the second derivative test for functions of one variable and goes by the same name, but instead of looking at just the concavity of a curve, the concavity of a 2-dimensional surface has more features than it does for a function of one variable. And we need to form what's called the discriminant of the function. So it's a function of a and b, d, which evaluates to a number, and it's equal to the second derivative in the x direction times the second derivative in the y direction minus the mixed derivative squared, evaluated at the point AB. If you're familiar with determinants, this is just the determinant, which might make it a little bit easier to remember. What does this tell us about critical points? There's a rule for using it. If d is positive, and either the second derivative with respect to x or the second derivative with respect to y is positive, then we have a local minimum. If d is positive and the second derivative with respect to x or the second derivative with respect to y is negative, then we have a local maximum. And the third possibility is d less than 0, and this is then a saddle point, like we saw before. If d is 0, there's no information from this test. So just a brief note, if d is positive, let's have a go at an example with this in action. Let's find all of the local extrema, which is to say the minima and maxima, and the saddle points of the function x squared minus 4xy plus y cubed plus 4y. First thing to do is find the critical points. We first find the x derivative and then the y derivative. And we're looking for points where both of these functions are equal to 0. The way to solve these is to try with the simplest first. So the first one, fx equals 0, implies x equals 2y. Along the line x equals 2y, the function has 0 change in the x direction. And now we substitute that into the derivative with respect to y. That derivative then simplifies to 3y squared minus 8y plus 4, which is just a quadratic in y, which we can solve, giving me y is 2/3 or 2, and therefore the critical points are when x is 2 times y, so we have critical points at 4/3, 2/3, and at 4, 2. So now in order to classify these, we just calculate the discriminant, and that's the second derivative with respect to x times the second derivative with respect to y, which is 2 times 6y, and we subtract off the mixed partial derivatives squared, which is minus 4. So the discriminant for this function is 12y minus 16. At the first critical point, this is minus 8, and because it's negative, this is just a saddle point. At the other critical point, the discriminant is equal to 8, greater than 0, and we check the sign of one of the second derivatives, take the easiest one, and that's also positive. In this case, we have a local minimum. And we can see these features on the surface given by the function.